okay? Let's just look, we looked here at the plane x equals 3, we got this. We looked at the plane x equals 1, we got a lower parabola. So we just go to any plane x equals x naught, where x naught is some number between 1 and 3. That doesn't even have to be between 1 and 3, but if it's going to be relevant to the region that we're looking at, we might as well assume that it is. The first thing we did, and it's of course been hidden by the next thing we did, but the first thing we did was we said, okay, let's just look at that segment between x naught negative 2, 0 and x naught 1, 0. That is, the y values go from negative 2 to 1, right? So if x is equal to x naught, the point x naught negative 2 down here in the plane would be x naught negative 2, 0 in 3 space. So the 0 is just there because we're in the plane. That would be this point. And x naught 1 in the plane, xy plane, would be here. So there's the line. Now, along that line, we have this section of the parabola. And then if we shade all that, understanding that that's a vertical object, okay, you see what the shape is. And that's consistent with what we've drawn over here and so forth. Now it's going to be that way for any x naught. If x naught is closer to 1, it's going to be lower. As we move to 3, it's going to be higher. The next thing we do, if we want to get a handle on volume, is we say, okay, well, let's just now assume that we have a small delta x interval, which I originally sketched right here. So there's an interval of the x-axis. And if we use that same interval for that delta x, it's a small delta x interval containing x naught. So here it is, goes on one side of x naught and to the other, and then the same interval can occur here and here. So now we've got a little tiny rectangle down here, a little thin rectangle whose x-coordinate includes x naught. We take the region of the object we're looking at above that little rectangle. Well, it's a thin rectangle. So the parabola we get at this edge of the rectangle is a little higher than the parabola we get at this edge. And the parabola that we get for x naught is somewhere in between. Okay? So we have a little higher parabola toward the front, a little lower toward the back, and the parabola for x naught in between. If delta x is very small, the difference between the parabola in back and the parabola in front is small. So we can say that this portion has a volume that's close to the volume of the region between the xy plane and the graph, okay, corresponding to this small region. And it's very close to the actual area of what you would get if you found the exact area above this rectangle. So we have a good approximation to the area above this delta x wide rectangle down here. And if delta x approaches 0, that approaches a perfect approximation for this function. So, what kind of an object do we have here then? Okay, if we allow this rectangle to be the same, or this parabola to be the same as this parabola, which is the same as this parabola, meaning the parabola in front is the same as the parabola in the middle for x naught, and the parabola in back is the same, so that this is now a cylindrical object. Okay, it's a cylinder. Now, a little bit of trouble with a cylinder because everybody thinks of a circular cylinder and usually a vertical circular cylinder as opposed to a circular cylinder maybe that's lying on its side, so it's like this, comes out toward you, or lying on its side this way, so it goes like this. A cylinder can be in any orientation. And the general definition of a cylinder is that it has cross sections perpendicular to an altitude, and the cross sections are uniform. And you need to distinguish it from a prism too, but I'm not going to go into all the geometrical details. Okay. The point is that this is a cylinder because it has uniform cross sections in planes parallel to the XZ plane. Okay? Now I'm not talking again about the actual region above this thin purple rectangle down in the XY plane. I'm talking about the approximation we're making, assuming that the cross sections are all the same. Okay? So we have uniform cross sections in this plane. The altitude is measured perpendicular to those cross sections. So we have to have an altitude perpendicular to our uniform cross sections, and then we have a cylinder as opposed to a prism where the altitude might not be perpendicular. Actually, the altitude still has to be perpendicular on the axis, and never mind. Okay. Now the general principle for the volume of a cylinder is not pi r squared h, which is something everybody memorizes and some people actually remember. That's a circular cylinder. Okay, a general cylinder can have any cross-sectional shape. And the volume of a cylinder, the principle is you multiply the cross-sectional area by the altitude. And there are very simple, obvious reasons why you do that. Should be obvious, and this should be shown, I think, better in our curriculum. So it's not pi r squared h, it's cross-sectional area times altitude. Now, if the cross-section happens to be a circle of radius r, then the cross-sectional area is pi r squared. And you can multiply that by the altitude, and you call the altitude h. So pi r squared h is perfectly good if you have a circular cylinder. This is clearly not a circular cylinder, so you can't apply that. But you can apply an analogy. If you want to understand pi r squared h as pi r squared, the area of the cross-section, multiplied by h, the altitude. Here, we're going to have to multiply the cross-sectional area by the altitude. Okay? So, what's the volume? Well, let's back up a second. And I didn't say it, but I did say it earlier. I said it in yellow before I did any of the purple stuff. What is the area of this region in the x equals x naught plane? Well, the function in the plane x equals x naught, well, if x equals x naught, then we have z equals x naught squared plus 3y squared, and we know we can get the area by integrating that function between the endpoints of the curve. Okay, the endpoints of the curve occur at y equals -2 and 1, and of course the curve is in the y versus z plane. So the area is just going to be the integral of that function with respect to y between y limits -2 and 1. Okay, so we know now we have an integral for our cross-sectional area. Now, we'd have to know what x naught is to find the numbers, but if we did, we'd easily be able to find them. This integral represents the area, and it represents the cross-sectional area now of this slice. Okay, this thin delta x wide slice of the region that we're trying to, for which we're trying to determine the volume. Okay? So now, this cylinder has cross-sectional area given by this integral, and it has a width, which is the altitude because it's perpendicular to the cross-section, delta x. So we multiply this integral by delta x, and we have the volume of this section, and then we just have to sum the volumes of all such sections up to get an approximation of the total volume. And of course, when we sum up sections like that, we're gonna let our delta x's go to 0, and we're gonna get an interval. So we'll do that next.